Hey guys, this is the actual guy Romit, and today I'll be discussing the single most important topic of subject CD3, that is the maximum likelihood estimation. Okay, and the reason I call this the single most important topic of subject CD3 is because this is the most widely used thing out of CD3 that is used in all the other actuarial subjects, and this has a lot of further applications. So, I think this is the topic that you should concentrate the most on and you should be thorough with. Okay, so without further ado, I would start with this topic, that is the maximum likelihood estimation, and I hope you enjoy and you learn a lot from this video. Okay, so talking about maximum likelihood estimation, what do we aim with the maximum likelihood estimation, or what do we intend to do? See, the problem here is that we have got a random variable, that is x, okay, and it has a certain distribution. This random variable has a certain distribution with the parameter theta, or there can be multiple parameters too, but for now I'm considering x that has a distribution with just one parameter theta. Okay, and this parameter theta, it is unknown. We do not know the value of this parameter. So all we have about x is a sample of values that are drawn from this random variable x. And let's call this sample x1, a small x2, x3, and going up till xn. And I've got this sample of values, and this is a sample. And I need to use this sample in order to estimate the value of theta. Okay, so I want to use the sample and estimate a value for theta. So one way I can do this is called as a method of moments estimate, or MME, okay, which is the topic right before this one. Method of moments estimate suggests that we equate the sample moments. We calculate the sample moments out of the sample, and then we equate it to the moments calculated from the random variable, and that is how we find the value of theta. For example, it suggests that we can calculate the sample mean, and we can calculate the sample variance, and then we can equate the sample mean or the sample variance to the formula of mean or variance for this particular random variable x, okay, and we can find the value of theta. But the problem with this method is that it is a weak method. The reason I say this method is a weak method is because of the limitations of mean and variance to summarize the entire data. See, mean is too influenced by the extreme value. So if I have a certain value like 10,000 or something like that in the sample, then the mean would be too influenced, and similar problems arise with the variance. And if we want to estimate one value for theta, mean would give a different value and the variance would give a different value if we have only one parameter. So this method is quite weak and disputed. A better method, that is the maximum likelihood estimate, MLE. This is a way stronger method, and this is perhaps the best method to estimate the parameter value from using the sample values. Okay, so what the MME does as a solution to this problem is that it says that the value theta hat, that is the estimate for theta, is that value of theta for which the probabilities of getting this sample are the maximum. So what MLE is saying is that theta hat is that value of theta. This estimate is that value of theta for which the probabilities of getting this particular sample x1 going up till xn, this sample is the maximum. Okay, so this makes this the most likely sample that would come out of this random variable x, right? So that is what MLE suggests. So what we mean here is that MLE is suggesting that we maximize the probabilities fx1, fx2 going up till fxn for this sample in, and that value of theta that we would get from maximizing these probabilities would be the MLE estimate for theta. Okay, so now how do we go about this? How do we maximize all these probabilities together? The best method for maximizing all these probabilities together is to maximize their product. Okay, so we multiply all these probabilities together and then we maximize them. So in order to do this, there is a function called as likelihood function that is constructed, and that function is a nothing but the product of all the probabilities. So the probabilities of x going from x1 to xn are all multiplied. The way this is written using a product notation is the product of this pi, big pi sign denotes a product of I going from 1 to n f of xi, right? So that is what the likelihood function is, and the rest of the part of this is to maximize the likelihood function with respect to theta, and that we do using obviously the method of maxima minima, taking a first order derivative, equating it to 0, and then getting the second order derivative negative. So that is how we maximize the likelihood function, and now we'll see how we do it practically and find the values for the estimate of theta. Okay, so let's just quickly take an example of maximum likelihood estimation in one parameter case. That is where distribution only has one parameter and we have to give an estimation for that. So let's assume that x has an exponential lambda distribution and we have a sample of x having values x1, x2 up till xn. Let's say this sample is okay, we have got a sample of 5 values: 5, 7, 6, 8 and 10. Okay, let's say these are the 5 values that we have derived out of an exponential lambda distribution. Let's say these are holding times or something like that, and we have to calculate the value of lambda using the maximum likelihood estimation. So we know that the PDF, that is the probability density function of x, is obviously lambda e to the power of minus lambda x. Okay. Now the likelihood function, if I want to construct the likelihood function, it would be obviously the same definition: product of I going from 1 to n, uh, the f of xi, right? So I just have to multiply this n times, right? So this would be the same as I going from 1 to n lambda e to the power of minus lambda xi. Okay, so now we'll just multiply this n times. So if I do that, it would be lambda into e to the power of minus lambda x1 into lambda e to the power of minus lambda x2 going up till lambda e to the power of minus lambda xn. Okay, so that is what I have here. Okay. Now let's just multiply this. So there are n lambdas being multiplied together. So they are lambda to the power of n, and then we have got e to the power of minus lambdas also multiplied n times, but with different xi's. So if I try to multiply all of these, their powers, that is xi's, they would add up. Okay. So minus lambda would come out to be common, and I'll have xi's added up inside. Okay, so this would go up till xn, right? So this is what I will get. Uh, Simply I can just write this as lambda to the power of n e to the power of minus lambda sigma xi, where I goes from 1 to n, right? So actually you could have just come from this step directly to this step, but just so you could understand how I got this, I gave you two more steps, right? So this is our likelihood function, and now we will try to maximize it. So in order to maximize this, see, first we need to differentiate it, and the differentiation of this function is a bit tricky because we are differentiating with respect to lambda, and there are two lambda terms here, and we'll have to apply the product rule. So in order to not go that way and simplify this bit, we're gonna use a trick. Okay, we are gonna use the fact that whenever fx is maximum, the log of the logarithmic function of fx is also maximum. So instead of maximizing the likelihood function, that is L lambda here, we are going to maximize the log likelihood function. This is the log of the likelihood function, and we will maximize this function. So I'll take a log of this term and then maximize it. So it's just the log of lambda to the power of n into e to the power of minus lambda sigma xi. Okay, so that is what I have here. Okay, simplifying this a bit further, this is the log of lambda to the power of n plus the log of e to the power of minus lambda xi, and obviously this n will come down, so this would be n log of lambda, and this minus lambda xi would come down to sigma xi would come down, and this log of e, it would become 1 because the log of e with base e is just 1, right? So we know that. Let's now differentiate this with respect to lambda. So this would be the different derivative of ln log ln likelihood of lambda with respect to lambda. Okay, and that would obviously be n over the log of lambda would be differentiated as 1 over lambda minus lambda into sigma xi. So sigma xi is just a constant, and the derivative of lambda with respect to lambda is just 1, so we'll have a sigma xi here. Now equating this to 0, if I equate this to 0 in order to get a value for lambda, lambda would be equal to obviously n over sigma xi. Okay, so you can just check that. If I will send xi this side, and then I will send xi under n, so this would be the value that you would get. Okay, now let's check whether this is a point of maxima or not. In order to check that, we need the second derivative, so that is uh, the second derivative of log of likelihood with respect to lambda, and that would just be minus n over lambda squared. So yeah, sure enough, this is less than 0 for a positive value of lambda, and this value is positive, we know. So this is the point of local maxima. Okay, and this is a point of local maxima, so this is the maximum value, or this is the value of lambda that maximizes the likelihood function. And if I try to use my values in order to get this uh, value of lambda, this would be called as lambda hat. Okay, because since this is an estimate for lambda, this is called as lambda hat. Okay, and if I try to get the value, it would be, I had n is equal to 5, I had 5 values, and they summed up to 36, right? All those values, the sample I gave you up here. Okay, I've given you a sample. Wait, let me check. Yeah, I have given you this sample. Okay, so if I add up these values, they add up to 36, and there are 5 values. So sigma x is basically the sum of all these, that is 36, and there are total number of 5 values. So your value for lambda cap, that is the estimate of lambda, is just 5 by 36. Okay. So this was your first example. I'm going to take one more example just so things are more clear to you guys. And this time, let's say X has a Poisson distribution with the parameter mu. Okay, so this time the parameter is mu, and this is the value we need to estimate, and X is following this distribution. So we all know the probability function fx is uh, obviously equal to e to the power of minus mu to the power of x over x factorial, right? This is the probability function that we have. Okay. Now the next thing we do is obviously determine the likelihood function, that is L mu. So it is nothing but just the product going from I to n e to the power of minus mu to the power of xi over xi factorial. Okay. Now if I simplify this, there would be n of these terms. These terms would be n, so I will have e to the power of minus mu, and they are all multiplied together. So they will just multiply together and their powers will add n times. So I'll have e to the power of minus mu n, and these terms will also be n. There would be n of these, but with a different value for xi. So there would be mu to the power of x1 into mu to the power of x2 into mu to the power of x3, going up till mu to the power of xn. So their powers will just add up again. So mu to the power of xi, sum of mu to the power of xi, going from I, where I is going from 1 to n. Obviously, you know that. Okay, and in the denominator I will have the product of I going from 1 to n xi factorial. Okay, so now I will take the log obviously, but before taking the log I want to point out one thing to you. You will see that when I take the log, these three parts of the likelihood function, this one, and this one, they will become separate terms, separated by plus and minus signs, right? So if when I will take a derivative of these, the term that does not contain mu, the term that does not contain mu will just differentiate to become zero, because it would be a constant term. That is, this term is a constant term here. Okay. So instead of writing this again and again, I will just not do the trouble, and I will send it to the constant part. So I can just write this as e to the power of minus mu n into mu to the power of sigma xi into c, that is the constant part, because this does not have any mu terms, and what I need is to differentiate with respect to mu terms. So this constant, when I take a log, it would become a separate term which would differentiate to zero, and you'll see it how. So the log of the likelihood function, I'll call it ln L. So the log is the log of e to the power of minus mu n into mu to the power of sigma xi into c. Okay, and then now taking a log, this term, it would obviously e would become 1, so I would have a mu n here, and this term sigma xi would come down, so this would be sigma xi into mu, log of mu, plus the log of c. Okay, I have got a log c here. See, this log c would eventually differentiate to 0. So taking a derivative with respect to mu, obviously I have a minus n here, and with this I've got a sigma xi over mu, and this would become 0. So now equating this derivative to 0 in order to find the value of mu, mu would be equal to, see, if I send n on that side, and then I just send it under this, so this would be sigma xi over n. Okay, so that is your value for mu, that is your mu hat. Okay, and now in order to check whether this is a point of maxima or not, I would take the second derivative, which is, sure enough, it is negative. So this is the point of maxima, And if you need an example for this, there is a question number 10.6 of your core reading, which is an example of this kind of a question. And there the value of sigma xi is obviously given as a 24, and n is equals to 10. So your estimate for mu is basically 24 over 10, which is nothing but 2.4. Okay guys, so the next thing I want to talk to you about is the two parameter case. That is, if x follows a distribution, any distribution with more than one parameter. Say there are two parameters, theta 1 and theta 2, and what we want is we want estimates theta 1 hat and theta 2 hat for theta 1 and theta 2 given sample values of x, that are x1, x2 going up till xn, right? So we have the sample and we want values of theta 1 hat and theta 2 hat given using the method of maximum likelihood estimation. Okay. So for this, I'll tell you what happens. See, now this now this likelihood function, it becomes a function of x, theta 1 and theta 2. So it has three parameters now, and we have two parameters which we need to estimate. Okay, and we'll be taking the log same as before for this likelihood function, and then we'll be differentiating it. But then this time we will be differentiating the log likelihood function first with respect to theta 1 and then equating it to 0. So we'll be taking a partial derivative first and then with respect to theta 1 and then equating to 0 and getting a value for theta 1 hat. And then we'll be equating it with respect, we'll be differentiating it with respect to theta 2, and then equating it to 0, we'll be getting a value for theta 2 hat. So we will be able to estimate both the parameters this way. What changes here is that the second derivative, okay, the second order derivative, okay, in order to check the point of local minima or maxima, that changes here. Okay, the thing is that calculation of second derivatives in case of two parameter case is a bit complicated, and it is done using a method called as the Hessian method. Okay, Hessian matrix is used, and I would love to discuss this Hessian matrix with you guys here. But the thing is that it is not covered in the subject CD3 curriculum, and it is a beautiful mathematical technique that helps us to, you know, check whether there is a point of there is a point of maxima in two parameter case or not. And if you are a mathematics or a statistics student, you must have understood this. Otherwise, even if you're interested, you can look it up on the internet, and there is a lot of content on this available, so you can go and understand this if you're curious enough. For now, for subject CD3 sake, you would not have to check the second derivative, or you would not have to check whether there is a point of maxima at this point or not. We are going to assume that it is so. Okay, so you just have to take the first derivative and then you have to equate it to 0 and assume that the second derivative is negative and it is a point of local maxima. Okay, so for this I'm going to take an example now, and I'm going to take the simplest possible example for a two parameter case, because other examples are really complicated, although they are often asked in the exam, and if you want me to discuss them, I will make videos on them too. But I'm taking a simple example right now, and the example is where x follows a normal distribution with parameters mu and sigma squared. Okay, so this is our distribution, and my aim is to find the maximum likelihood estimation for mu and sigma. Okay, so that is what I am going to do. Okay, so the likelihood function, same as before, would be I going from 1 to n f of x i's, right? So this would be the same as I going from 1 to n. The fx for normal distribution as we know it is obviously 1 over n, 1 over sigma into 2 pi into expectation of half xi minus mu over sigma. This is given in the tables, you know that, right? Whole square. So this is the probability function for a normal distribution, right? So I'll be using this here. So this is 1 over sigma into 2 pi into the exponential function of half xi minus mu over sigma whole squared, and this is what we need. Okay, now I'll simplify this further. Let's simplify this. Okay, we know that 2 pi does neither contains mu nor sigma, so this is a constant term that is multiplied with these. So I'm going to send this into a constant. I have got a 1 over sigma to the power of n because there are n of these multiplied. This is a small n. I'm sorry. Okay. So there are n of these multiplied, and I have got n such exponential terms. They are multiplied together. So all of their powers are added together, right? Like before. So this would be e to the power of sigma minus half. Okay, I'll take the sigma outside, so that would be sigma squared, and inside I've got a xi minus mu whole square, right? So these are the two terms that I have now. Now I'll take a log. So the log likelihood function looks somewhat like this. Obviously, this n would come outside and it would be a negative because this is 1 upon sigma. So that would be minus log sigma, and then log of this would obviously be 1, and whatever is in the power would come down. So this would be sigma I going from 1 to n uh, minus 1 upon 2 pi 2 to square. Okay, yeah, this is it, and I've got a xi minus mu whole square. Okay, so this is what I have, guys, and since this is a constant, I'm going to now take it out. So this is n into log of sigma minus 1 upon 2 sigma squared, and I is going from 1 to n xi minus mu whole squared. Okay. So the first thing that I want to do is find a value for the estimate of mu, right? So because that is the first parameter, you can do it in either order. You can first do it with respect to mu or sigma, but I'm going to go with the standard order. So I'm going to do mu first. So this is the differentiation of log L with respect to mu, and remember this is a partial derivative. So sigma here is basically acting as a constant. Okay, so let's do this. This is minus n over sigma. No, this would be 0 because these are both constants. Minus, this is a constant term, so I'll keep it outside. And differentiating this, uh, although there is a summation sign, differentiation is pretty straightforward. 2 comes down, and I've got a sigma I going from 1 to n xi minus mu, right? You got it, right? So I will just equate this to 0 now, and what happens here is there are two terms multiplied. So if this has to be equal to 0, that implies that either minus 1 over 2 sigma squared is equal to 0, which is not possible because then sigma squared would be an undefined value, or sigma xi minus mu is equal to 0, right, which is possible. So we will take this into account. That would mean that sigma xi minus, since this is a constant, summation makes it n times because I've got n terms here going from 1 to n. So this is n mu is equal to 0, which implies that sigma xi is equals to n mu, and that implies that mu is equal to sigma xi over n, or it is just equal to the sample mean, right? As you would have expected, the population mean is equal to the sample mean. This is a result which you would have derived from method of moments estimate too, right? uh, with the second part, that is with sigma, I will take a derivative again, so that would be sigma ln of L with respect to sigma, right? Let's differentiate this. This is a bit more complicated than the last part. So let's see what is happening here. Here I will have n over sigma, okay, and I will have this is sigma to the power of minus 2. So minus 2 will go upstairs, and I will have a plus here, and this will become 2 sigma to the power of 3. So these two cancel out, okay. And what I will have inside is just this constant term. So this would remain the same constant term, that is sigma um, xi minus mu whole squared. Okay, so this is what I have. Now I will equate this to 0. Obviously this would be 0. So equating it to 0, um, obviously for this to happen, either I can take 1 upon sigma common out of this. So either 1 upon sigma is equal to 0, or minus n plus 1 upon sigma squared into sigma xi minus mu whole square is equal to 0. So this is the more logical option, since with this sigma would become an undefined number. So that is what will happen. So I'll calculate a value for sigma, and that value would turn out to be a root over sigma xi minus mu whole squared over n. Okay, so that is the value that we have. Perfect. Right. So how will we proceed with this? First, we will calculate the value of mu, that is equal to the mean of the sample values, and then we'll put that value here, and we will find out sigma. And obviously this is also very obvious. This is just the direct formula for standard deviation that you would have expected. See, this is sigma xi minus x bar over n, and this is rooted, right? So that is how it works, okay. And that is all about the two parameter case, and you don't need to take a second derivative here. We just assume it to be negative, and it is usually done using the Hessian matrix, which is not a part of the subject CD3 curriculum. So the next thing I want to discuss with you guys is a special case that is of a uniform distribution. This is given in your core reading. So let's talk about it. Okay. The problem with the uniform distribution is what I will be presenting you right now. Why the standard likelihood method cannot be applied, and here we will be applying something called as common sense, which is very uncommon these days, but we'll still try to use it. Okay. So how will we do it? Yes. So let's say we have got a bunch of values x1, x2 going up till xn, and these follow a uniform theta distribution. Okay, so that is what they follow. They follow a uniform theta distribution. For this to be true, something is necessary. Okay, the thing is that these values xi going up till xn, all these values should be greater than 0, obviously, because 0 is not even a valid value in a uniform distribution, and all these should be less than or equal to theta. And the reason I say this is you can think about a die. Okay, you can think about a die. A die, I'm sorry, a dice. Dice, that is what we call it. Okay, you can think about a dice. Okay, a dice has one, two, three, four, five, and six. Six heads. Okay, it has six heads with all these demarcations on it, right? And uh, the probability of getting any of this is 1 by 6, and theta in case of a die is obviously it is 6. It is the highest value here. So any value you will get out of this die would either be 1, 2, 3, 4, 5, okay, 6. All these values are either less than or equal to 6. Okay, so this needs to be true. All these values, or whatever value of sample you might get, all these values would be less than or equal to theta. Okay, so that is something you need to remember. So now x is following a uniform distribution, and we know that the probability function f of x is obviously equal to 1 upon theta for each value of x. Okay, so the likelihood function obviously would be obviously I going from 1 to n 1 over theta, right? So this is multiplied n times, so this would be 1 over n theta to the power of n. Okay. Now what happens if I try to take a log and then differentiate it? If I take a log, then ln of L would be equal to minus n log of theta, right? That is what it would be. And if I take a derivative of this, n ln over del theta is equal to minus n upon theta. And if I equate it to 0, I get an absurd value for theta, that is theta is equal to infinity, right? And that is quite absurd. In order to maximize this, we need theta equal to infinity, which is not possible, right? Which is absurd. So this method is not possible here. What we use here is common sense. Let's think about it. Okay, I need to maximize this function 1 over theta to the power of n. Okay, so this function, in order to maximize this, obviously I would need as small a value of theta as possible. We know that 1 over 0 is equal to infinity. So the smaller the denominator, the larger would be the number, right? So we need the value of theta to be as small as possible. And the smallest value of theta that is possible for this given sample x1, x2 to xn would be the largest of these values. So, so I because the reason for this is that as I said, these all these values, all the sample values, they need to be less than or equal to theta. So theta can at minimum, because I need the smallest value of theta, it can be at minimum the largest of these values. Okay, so what happens here is that theta is equals to the maximum of x1, x2 going up till xn, right? So theta would be the maximum of these, and that would be the value which would maximize your likelihood, and that is the value you need. So if I have a bunch of numbers coming out of a uniform distribution, 2, 3, 5, 7, 9, okay, so theta is equal to the maximum of these values, that is 9. Okay, and all the probabilities would be 1 over 9, that is 1 over theta. Okay, so the next thing we talk about is a topic called as incomplete samples. See, what was happening so far was that the data sets or the samples that were available to us, x1, x2 going up till xn, this was a complete sample or a complete data set. So this gave us information about all the possible values that x can take, okay, if it was large enough. Okay, so this ranged over all possible values of x, right? But now a certain thing can happen, that we can also have incomplete or truncated or censored samples. So incomplete data can be of two types. It can be either truncated data or it can be censored data. In case of truncated data, we have no information about a certain set of values or a range of values. Okay, so the best example I can give you in order to explain what truncated data is, for example, there is a claims department of a life insurance company, and it is observing the number of claims on a policy. So, for example, it has a bunch of policies, it has thousands of policies, and it is observing the number of claims that are arising on these policies. But let's say they have no data about the policies with no claims. Okay,
So they only know about the policies which have one claims or two claims or three claims or four claims, or however much may they accept, but they do not know about the policies which do not have any claims, right? Because it can so happen that the claims department does not even get the information about those policies on which no claims arise. So this is an example of a truncated data, that we do not know those policies which are for which x is equal to 0, right? We do not know the number of policies on which there are no claims, right? So this is an example of truncated data. Let's talk about another thing, that is censored data. In case of censored data, this is different from truncated data. We do not know the exact values. Okay, we do not know the exact values of a range of policies, but we know that they exceed or they are less than a certain number, or they are between two limits. Okay, some kind of information is available. In case of truncated data, we have no information about the set of values, but in case of censored data, we have a certain information. Let's see how. In case of censored data, the best example would be the best example would be a researcher who is observing the lifetime of a certain variety of rodents for 1 year. Okay, so there's this researcher. He has got 15 rodents with him. Okay, 15, let's say mice or maybe guinea pigs or something like that. He has 15 of these rodents, and he is going to observe them for 1 year and note their lifetimes. Okay, so by the end of year one, he can have like 12 guinea pigs dead and 3 alive. Okay, so this would mean that we would know the exact lifetime of these 12 guinea pigs. He would know the exact lifetime. He can know that one died at 0 times 0.5, one died at times 0.7, and so on and so forth, right? He can know the exact value of these. But for 3 guinea pigs which are alive, he is no more going to observe them, because the period of 1 year is over, right? So for these 3 guinea pigs, all he knows is that their lifetime exceeds 1 year, right? They have a lifetime of greater than 1 year, and he has to give his observation taking into account the entire data. That is, all 15 guinea pigs are to be taken into account. Okay, because if he takes only 12 into account, that would be, injustice to the data, and that would give us a biased estimate. So in order to get our best estimate, we need to include all 15 guinea pigs, or we need to include the entire data. Okay, so let's see how do we do that using a maximum likelihood estimator, and how do we get a maximum likelihood estimator in case of a incomplete sample. So for example, first thing I'm going to discuss with you guys is for censored data. Okay, so for censored data, the likelihood function changes somewhat like this. For example, in this example of a researcher, uh, he knew about 12 guinea pigs, and he did not know about 3 guinea pigs. So let n is equal to 12 and m is equal to 3, right? Let these be the values. So the likelihood function would now be the probabilities of these 12 guinea pigs multiplied, right? The probabilities of these guinea pigs multiplied from 1 to 12, uh, and that would be the probability function, which would be multiplied 12 times, and that would be multiplied for these 3 guinea pigs with the probability that their lifetime exceeds 1 year, right? So for these 3 guinea pigs, it would be multiplied with the probability that their lifetime is greater than 1 year. So u here is equal to 1. So this is what the likelihood function would look like. It would be the product of all the probabilities for which the data is available, and for um, all the probabilities for all the data points for which the data is known to exceed a point. It would be the probability that such data exceeds that point, and this would be multiplied, because there is a power of m here. It would be multiplied by the number of data points, right? So that many times it would be multiplied. Okay, so if I have 3 guinea pigs exceeding the time of 1 year, so this would have been p into x is greater than 1, to the power of 3, right? Something like that. And for these 12 guinea pigs, I would have had p into x is equal to whatever their lifetime is, xi, and it would be these would be multiplied going from 1 is equal to 12 for all these guys, right? So that would be the likelihood function. That is how it will function. Okay. So that is how it functions, right? For censored data. Now let's take an example. How will you solve questions based on these? And I am sure it would be clearer to you how it works. Okay. So I've got a question from the core reading itself. Uh, there is a question from the core reading itself. Okay. I don't know the number of the question. You can check it out. It is the first question for censored data. Okay. So let's work out this question. So it says that the waiting times in a post office for a queue have an exponential lambda distribution, right? So exponential lambda distribution is followed by the waiting times, right? Exponential distribution is followed, and 10 people had their waiting time. So we know the exact waiting time for these 10 guys. Okay, 10 people, we know the exact waiting time. But for the further 6 people, uh, had waiting times of more than 4 minutes. Okay, so we have got all these values less than 4, and we know the exact values. And for we know 6 people, the waiting times were more than 4 minutes. So, and based on these data, find the maximum likelihood estimate for lambda. So we need to find the maximum likelihood estimate like we used to before. This is the question that we have. Let's start constructing the likelihood function. So the likelihood function would look somewhat like this. Pi, product of I going from 1 to obviously n f of xi into the probability that x is greater than let's call it L for let's say m number of values. Okay, so this is what it looks like. Now let's see, and we know that m and n are equal to some values. N are 1 2 3 4 5 6 7 8 9 10 10 values. So n is equal to 10 and m is equal to 6, right? So we have got a total of 16 people here. Okay, so for these 10 people, so I going from 1 to 10, I have got the probability function of a Poisson distribution with the parameter lambda, that is lambda into e to the power of minus lambda xi, right? And for these remaining guys, it is the probability that x exceeds 4 for these guys, okay, for to the power of m. So we know that f of x, that is the probability that x is less than equal to x for exponential distribution is 1 minus minus lambda to the uh, to the power of x. This is the probability. So probability of x being greater than x is 1 minus this, so it is e to the power of minus lambda x, right? That is what this is, where x is the value of that particular value which these values are supposed to exceed. Okay, so it is e to the power of minus lambda into 4 and whole to the power of 6. Okay, so that is what I have here, right? So let's start solving this. Let's see what we get. This is multiplied 10 times, so I've got a lambda to the power of 10. This is also multiplied 10 times, so the xi's would add up together because all the powers would add up together. So this is e to the power of minus lambda sigma xi, where I goes from 1 to 10, right? That is how it will work. And for this one, I will just have e to the power of minus lambda to the power of into 24, right? 6 4 is 24. So this is what I have here. Let's take the log of likelihood function. So ln L would be equal to 10 log lambda minus lambda into sigma xi minus lambda into 24. Okay, so this is what I have here. Let's take the derivative. Derivative of log with respect to lambda is just 10 upon lambda minus sigma xi minus 24. And then equating this to 0, I have got lambda is equal to sigma xi plus 24 and 10. Okay, yeah, 10 is divided by sigma xi plus 24, right? This is what I have here. This is my final answer. And putting the values of sigma xi and 20 xi here, I will get, what was the sum of xi's? So this value is 18.3 and this is 24. So my final answer is 10 divided by 18.3 plus 24. That is 0.2364, and in decimal terms it is 100 upon 423. Okay.
And the second derivative, that is d2 ln L over d lambda squared, that is obviously negative. It is minus 10 upon lambda squared, right? So this is less than 0 and thus this is negative, and this is the point of maxima. So this is your value for lambda hat. So this is lambda hat. Okay, now let's just solve an example on truncated data. We already did one on censored data. Let's do one on truncated data, and this is example 10.7 from your code reading. Okay. So this says that the number of claims in a year on a pet insurance policy are distributed with the following distribution. Okay. So the probability of getting zero claims on a policy is 5 theta. That getting one on a policy is 3 theta. That of getting two on a policy is theta, and three or more is 1 minus 9 theta. Okay, so these add up to 1. Obviously, this is a discrete distribution, and there is information from the claims file that showed that there were 60 policies with one claim, 24 policies with two claims, 16 policies with three or more claims, and there was no information about the number of policies with no claims. So this is very similar to the example I had given you earlier, that they don't know, they don't have any data about the policies with no claims, right? So this one is not available. So first we need to transform this distribution in such a way that this part, this zero policies part, is eliminated. So the number of claims and the probability that n is equal to n. Okay, we have got these two things, and this is denoted by n. So we don't have anything for 0. We have data for 1, 2, and greater than equal to 3. Okay, and this is equal to 3 theta. This is equal to theta, and this is 1 minus 9 theta. Now I don't have any data for 0. So what I do here is I need to convert this into a proper probability distribution. And for that, all I need to ensure is that all the probabilities for each of the value, that is probability x is equal to x for all x's, is not equal to 0. That is the first thing, and that the sum of all the probabilities of x is equal to 1. So I need these probabilities to add up to 1. So let's check their sum now. Their sum now is 1 minus 5 theta, right? So in order to make it 1, I will divide all these by 1 minus 5 theta. So it would become 1 minus 5 theta divided by 1 minus 5 theta. That would be 1. Okay, so in order to make this a proper probability distribution, I'm dividing all these probabilities by 1 minus 5 theta. So this is 3 theta over 1 minus 5 theta. This is theta over 1 minus 5 theta. And this is 1 minus 9 theta over 1 minus 5 theta. Right? So that is what will happen. Now this is a proper probability distribution. Let's talk about the likelihood function. So likelihood function is only a function of theta. It would be equal to the probability that n is equal to 1 to the power of however many values we have for 1. So we have got 60 claims with one 60 policies with one claim, and then for 2 we have got the n is equal to 2 to the power of, we have got 24, and the probability that n is equal to let's just say 3. Yeah, it is greater than equal to 3. Okay, greater than equal to 3 is to the power of 16. Okay, so this is what we have, and this probability is 3 theta over 1 minus 5 theta whole to the power of 60, and this is theta over 1 minus 5 theta whole to the power of 24, and this is 1 minus 9 theta divided by 1 minus 5 theta whole to the power of 16, right? So that is how things are here. Okay, all right. Now the next thing we do here is that okay, um see this 3, it goes into a constant, and I'm gonna multiply all the theta terms here. So the theta terms, there's a 60 in the power of theta, and there's a 24, so that becomes 84. And then I've got a 1 minus 9 theta to the power of 16, and in the denominator I've got a 1 minus 5 theta to the power of 60 plus 24 plus 16, that is 100. Okay, so this is my likelihood function, right? Now I will take a log for this. So the log of likelihood function is 84 log theta plus 16 log of 1 minus 9 theta plus 100 log of 1 minus 5 theta. Okay, so this is what I have here. Now let's just differentiate this. Let's just take a derivative of this thing with respect to theta. Okay, so taking a derivative, this is 84 over theta. This is 16 over 1 minus 9 theta into minus 9, and this is 100 over 1 minus 5 theta into minus 5. So if you will try and simplify these terms, and I am writing the result directly for you guys, you can simplify them. If you take an LCM, eventually what you will get here is 84 minus 82 theta is equal to 0. Okay, I simplified it and gave you the answer directly. You have to simplify it, and this gives the value of theta hat as obviously 84 upon 82. I think this is not right. There's something wrong with this. Okay. I think this is 820. Okay. This is 820. Okay. So 84 over 820, and this would be 0.102, right? And if you would take the second derivative, d2 ln l theta over d theta squared, this would surely will come next less than 0. That would imply a maxima. Okay, I'm not doing these parts. I've already taught you how to do these. I'm giving you the results directly. Okay, so this is the value for theta that you need. Okay, so guys, this is the last topic that I want to discuss with you, and this is given in your core reading, and it is called as independent samples. Okay, so what this means is that now instead of having only one sample, we have got two samples which are independent on each other, but they are based on the same parameter. Okay, they have got similar parameters, and we have to use both of the samples in order to calculate the value of the parameter, because we always intend to use the entire data. So I'm going to discuss this using this example from your core reading. This is example number 10.8 from your core reading. So this says that the number of claims X per year arising from a low risk policy has a Poisson distribution with a mean mu. and the number of claims per year arising from a high risk policy has a Poisson distribution with a mean 2 mu. Okay, so there's this low risk policy and there's this high risk policy, and they have got uh, parameters, and X has a lower parameter. This leads to a lower number of average claims, and Y leads to higher number of average claims as expected. Okay, so it says that a sample of 15 low risk policies had a total of 48 claims. Okay, and a sample of 10 high risk policies had much more. They had a total of 59 claims, and they want us to find the maximum likelihood estimate mu based on this data. So the likelihood function here would obviously become the product of both the likelihood functions. It would incorporate the likelihood functions from both the samples, and then they will be multiplied together to get a combined likelihood, and that would be used to estimate the value of mu. Okay, so let's start with that. So L theta, which is the combined likelihood of both of them, it is nothing but the product of the likelihood of both the samples. Okay, so for the first sample I going from 1 to we have got 15 values here in the first sample. Okay, that is of X, so it would be mu xi, mu to the power of xi into e to the power of minus mu divided by xi factorial. Obviously this is the PDF of Poisson distribution. For the y variable, it would be a j going from 1 to 10. There were 10 policies here, and it would be mu to the power 2 mu to the power of yi into e to the power of minus 2 mu over yi factorial, yj factorial. I'm sorry, j. So this is a j here. Okay. So now we simplify this. Try to simplify this. If we do that, this xi and yi factorial, they just go into the constant, and we are left with mu to the power of sigma I going from 1 to 15 xi, because there are 15 of these terms multiplied together, and e to the power of minus 15 mu. Okay, because they are multiplied, their powers are added up, all same, into 2 mu whole to the power of I will have a sigma y, a sigma j going from 1 to 10 here, and there would be a yj here, obviously, and this would be e to the power of minus 2 mu into 10, right? That would be 20 mu. Okay, so this is what I have here. Now let's just do one thing. Let's take a log of this. Okay, so the log of, let's just combine them first. Let's just combine them first. So we have got this 2 is a constant, so I've got mu to the power of sigma xi going from 1 to 15, and sigma yi. Okay, I've got these two things, and I've got e to the power of this is a 20 and this is a 15, so I've got e to the power of 35 mu minus 35 mu. Okay, so this is what I have. If I take the log of this likelihood function, so ln of L theta is nothing but sigma xi plus sigma yi into the log of mu, okay, minus 35 mu, because this would become just 1. Okay, so this is what I have. Now differentiating this with respect to, I'm sorry, this is L of mu. Okay, this is not L theta, it's L of mu. Okay, so differentiating with this with respect to mu, I'll have the differentiation of log of L mu with respect to mu, that would be equal to sigma xi plus sigma yi divided by mu minus 35, and this would be equal to 0, and I would get mu is equal to sigma xi plus sigma yi divided by 35, and we know that the value of sigma xi, x has led to 48 claims, and y has led to how many? Y has led to 59 claims, and this is just 35. So I've got a value for mu here, and the value is 107 divided by 35. Okay, and if I want to, so this is your mu hat. Okay, and if I want to check the second order derivative, that would be simply minus sigma xi plus sigma yi divided by mu square. So that is a negative thing, and thus this is a point of local. This is a point of local maxima for me. Okay, so that was all about maximum likelihood estimation, guys. Thank you for watching, and I hope you enjoyed the video, and please comment, subscribe, share. And if you want me to make an entire course on subject CD3 like I have done on subject CD5, you can contact me. You can comment on my YouTube page, or you can contact me on Facebook. There are a lot of ways to contact me. Okay, just get in touch, or cheers. All right, goodbye.